Our universe certainly seems real. But what if it's not? We may be nothing more than video game characters designed for someone else's amusement. But how could a computer juggle every aspect of the cosmos? Maybe what looks random has already been programmed to happen. Can we discover some hidden glitch in the laws of the universe and uncover its hidden code? Do we live in the Matrix? Space, time, life itself. The secrets of the cosmos lie through the wormhole. Pick up a rose, take in its scent. Feast your eyes on the crimson of its petals. Feel the prick of its thorn on your finger. These sensations are what ground us in reality. But what if they're just fabricated? What if we are merely players in someone else's video game? The Big Bang just the moment someone flipped the switch and turned on our universe. In the movie The Matrix, there was one way to see the truth behind a fake reality. Take the red pill. Are you ready for it? Jesse Shell knows a lot about video games. He teaches students at Carnegie Mellon University how to design them. He appreciates the enormous effort it would take to create all the details of our world inside a computer. The most sophisticated video games are still played on two-dimensional screens, like the one you're watching now.
Creating the illusion of 3 dimensions on flat screens is much simpler than actually creating real 3-dimensional space that we can move around in. So programming 3D space as we know it would be many, many orders of magnitude more difficult than anything we know how to do right now.
Jesse and other video game designers are pretty good at simulating the way objects move through space. They use Newton's laws of gravity and motion, just as the designers of our world would.
The balls have weight, air is moving around them, electrical charges are increasing and decreasing on the surface of each ball, and even if I'm a little bit off, the laws of physics are still intact. But if the rules themselves are off, then we'll know right away that something's wrong, that it's not an accurate simulation of our world.
Making a believable reality would take far more than perfect programming of the way objects look and move.
You'd have to program all the other senses too. Sound, smell, taste, and touch, and all the subtle variations. And if even one small thing was off, like say this coffee having the same taste and temperature as this cereal, you'd know right away that something was terribly wrong.
How would you computerize taste? Or program the feel of soft grass underfoot? Even the air we breathe is filled with gases, water molecules, dust particles, and pollen. At Carnegie Mellon's Entertainment Technology Center, Jesse is trying to make simulations as immersive as possible. In what he calls the cave, a moving platform adds to the visual experience.
But sometimes the simulation is too much for the computer, and we get glitches, just like in a video game. It's possible that if we were making a simulation of the real world, that the same thing could happen.
When a computer can't keep up with the visuals it needs to render, you often see a defect called screen tearing. We've never seen that in our world, but not all glitches would be visible to people on the inside.
If the simulation freezes, then the people who are in it might not know, because it could freeze for 1,000 years, and anyone who was part of the simulation would also be frozen in a state of suspended animation, so that when it started up again, it would be absolutely seamless to them, and they would never know.
If someone else has created us inside their computers, then they must also have built programs for all of our mental abilities. Our imaginations, our emotions, and the thoughts running through our heads every time we engage in conversation.
As humans, we get so much information from talking that an accurate conversation program is crucial.
What did you want to be when you grew up?
A fireman.
A fireman? That's noble. So either A, you've got a death wish, or B, you like to stare at fire.
And it only takes us a split second to notice a problem with a conversation. So you can imagine the challenge of simulating 7 billion people all talking together at once.
Jesse thinks our creators could be using a few shortcuts to handle this heavy load. Concepts already used by today's game programmers.
You could make just a few people the active players and then surround them with billions of much simpler characters. Or another thing you could do is only put detailed simulations where I'm looking at a given time. If I'm looking just to one place, just put all the focus over there and make everything else around me just kind of a blur.
Maybe you are the only active player in this game you call your life. Everyone else exists only when you are paying attention. Your program would be the only one running all the time, even when you sleep.
Dreams are already a kind of simulated reality. So to program dreams, you'd have to create a virtual reality within a virtual reality.
If our world is an incredibly complex computational creation, what does that say about its creators? What must their reality be like if spawning an entire universe is just a game?
As difficult as it is for us to imagine creating a universe as complex as our own, it might not actually be that hard for someone living in a universe more advanced than ours. I think I'll need to sleep on that idea.
If we are living in a simulation right now, who created it? God? More advanced alien life forms that dreamt us up to be their avatars? Or could our creators be future versions of ourselves? Nick Bostrom, a professor of philosophy at the University of Oxford, believes we are almost certainly living inside the computers of our descendants.
The buildings here in Oxford are really old. This wall might be 400 or 500 years old. And think of all the technology we have developed in these short centuries. So if we zoom forward a few centuries, then presumably we will then have technology that will be equally magical to us as television would be to our ancestors who built these walls.
Nick believes over the next few centuries we'll be combining technology with our own biology. We will evolve into post-humans, hybrids of man and machine with phenomenal computational powers. Just 20 years ago, a realistic simulation of the city was impossible. Now we can make those fake scenes pretty convincing. The combined processing power of post-humans would have no trouble rendering an entire world and all the people in it.
We can estimate the amount of computing power it would take to simulate one human brain. And it's possible to calculate how much computing power a technologically mature civilization would have at its disposal. A mature civilization would have vastly more computational power available than it would take to run a full simulation with all 7 billion people in it.
Creating a virtual version of our world would be as easy for post-humans as snapping a finger. But why does Nick think our descendants have already done it? This priceless, real human skull was used in the very first performance of Shakespeare's Hamlet. Here hung those lips I have kissed, I know not how oft. Actually, it's only a cheap reproduction. One of many thousands used in the countless times the play has been performed. What if each of us is like that skull? There's one original biological version and thousands of fabricated copies. What are the chances that I am the original version of me? Or that you are the original version of you? University of Oxford philosopher Nick Bostrom is trying to get himself into the mindset of our superintelligent post-human descendants. He thinks their vast computing power will allow them to create virtual realities and watch them as easily as we watch TV.
Imagine that I'm one of these post-humans. I may decide to run elaborate simulations for scientific purposes, or maybe for entertainment. Think of these as the most incredible stage adaptations ever created.
Discordance. A family cleft in twain, my wife, like skull, without a brain. Boy!
Aye, father, thou call'st me?
What sayest thou upon the matter?
William Shakespeare simulated the story of a Danish prince named Hamlet some 400 years ago. 400 years in the future, when our descendants have the dramatic urge, they may make simulations of us.
What else do you speak?
With all of these capabilities that post-humans would possess, I could continually refine these simulations until they match the reality of my ancestors.
All right, stop.
So how likely is it that we are merely patterns of data on a post-human hard drive? Nick and a colleague have made the calculations, and the results are unsettling.
It's a strange message.
If my post-human civilization has the ability to create one incredibly accurate simulation of my ancestors, then we'll soon have the technology to create thousands, even millions of variations of this simulation, to examine all possible variations of our past.
Are we biological beings living here and now in the 21st century? Or is this actually the 25th century? And are we one of many simulated copies of post-human ancestors? Nick says the odds against our being biological humans are overwhelming.
It's like the odds that I'm watching this play the first time it's ever been performed. It's much more likely that I'm watching one of the many thousands of times it's been performed over hundreds of years. Cut! Nicely done.
If Nick is right, we'll need to get used to the idea that our lives are just computer-fabricated dramas. Let's hope our creators are enjoying the show. Could something as complicated as a human being ever be computer simulated? The characters we play with in video games have come a long way over the years, from bodies made of crude pixelated blocks to increasingly lifelike versions of ourselves. But even the most realistic avatars only look real on the outside. Could we ever build a body from the inside out, cell by cell? And could that simulated person be an exact copy of a flesh and blood human? Stephen Larson wants to build the world's first fully digital animal, a perfect replica of its biological counterpart. He's starting small.
All around the world, you can find a 1 millimeter long worm, much smaller than a typical earthworm. This barely visible worm is known as C. elegans. Now, it may seem insignificant, but this little guy has the distinction of being one of the most thoroughly studied animals in all of biology and neuroscience.
Stephen and his colleagues are compiling decades of research about this tiny worm in order to create the world's most realistic computer-generated creature.
It only has about 1,000 cells, 959 to be exact, and only 302 neurons, about 95 body wall muscle cells.
That sounds easy enough to build, but it's not. Each cell needs to run its own specific computer code, and all the pieces of code must function together just as the connected cells do. When finished, it won't just look real, it will act real. It will seek virtual food, produce virtual waste, and create virtual offspring. And making it will not be child's play. This little remote-controlled car only has about 1/10 as many parts as C. elegans.
Now here, We have a full-size car made of thousands of parts, including computers and wiring. It does all sorts of complex things like navigation, air conditioning. It has lights.
A worm's components are interconnected, just like those of a car.
In our worm, in addition to building muscle cells and nerve cells, we're also creating models of how muscle cells work together and how the nervous system should work. Then we can connect the muscle cells to the nervous system. Now, when we do that, this may be the result. Nothing, because of all the complex interactions.
But if Stephen and his colleagues precisely simulate every cell of C. elegans and get all those individual programs working together, his computerized worm will do something no car can. It will live and act completely under its own control.
It's a much bigger challenge than just programming flashy video game characters that look like real-life approximations of creatures. If we wanted to, we could already program a C. elegans and make it look like it can do all sorts of amazing things.
So far, Stephen and his colleagues have written programs for some of the worm's muscle and nerve cells. But they're still working on code to simulate the complex electrical and chemical interactions between them.
So we still have a lot of work to get everything built, wired, and connected together so that our virtual worm will behave just as a real biological worm.
Then the stage will be set to work on more complex creatures. A human is made up of trillions of cells. So creating one biologically accurate computer-generated person would be like wiring together all the parts in more than 100 million cars.
It may take many decades or even centuries, but I believe that one day we should be able to build virtual versions of ourselves that are like us in every way. So we'll have to get used to the idea that virtual or artificial entities may someday think and act for themselves. Hey, wait!
If we're already living in a virtual reality, then we must be those lifelike artificial creatures. But how can we prove it? This physicist believes he's found a glitch in the workings of our universe that could show us the Matrix is a reality. Artificial environments are built on a 3D grid. If someone built our universe in a computer, we should be able to find this grid underpinning everything. We've never seen any sign of it, but one scientist thinks he knows how to look under the surface of the cosmos to determine if there is an artificial wireframe holding reality together. Silas Bean, a nuclear physicist at the University of Washington, thinks about the grid like a football field.
A football field is known as a gridiron because of all the yardage markers. Now, if you imagine extending those yardage markers from sideline to sideline and from end zone to end zone, and further extend those grid lines into the third dimension above the field, then you have a grid or lattice structure, which is very similar to the foundations of the environment of a video game.
We instinctively think of the space around us as continuous and indivisible. Space doesn't appear to come in cubes, but in a digital reality, it would. Our grid would have to be smaller than the smallest thing we know, a subatomic particle.
There will still be minute distances between the points on the grid that are connected to each other. If we're living in a simulation, then this is what space-time could look like. Space will always be in discrete pieces rather than continuous.
Such a fine-grained 3D grid would be impossible to notice in our daily lives. It would even elude almost all scientific experiments. But Silas and his colleagues have devised a plan to detect it, if it exists. He thinks the most explosive events in the universe might give it away. Supernovas generate streams of super high-energy cosmic ray particles. But physicists have noticed something strange about them. The highest energy cosmic rays they expect to see are missing. Silas thinks the grid might be the culprit.
If reality is real and there's no artificial structure to our universe, then there is no upper limit on the energy than a cosmic ray particle can have when it is first created. But there does seem to be a limit, what we call the cosmic ray cutoff.
If cosmic rays are restricted to moving only along grid lines, it could act as a brake on their energy. To test this theory, Silas and his colleagues want to compare the energy levels of cosmic rays traveling in different directions.
Imagine if each of these band members is a cosmic ray particle. We can learn a lot by observing their motion. In a universe without an underlying grid structure, particles move the same way in all directions. Now let's see what happens if we assume that there is an underlying grid structure.
Moving straight along a grid axis is simple, like the path of band members in the blue uniforms. Moving diagonally, like those in white uniforms, requires a series of zigzag steps. That means they would have to expend more energy getting from point A to point B, compared with cosmic rays moving along an axis.
Another way of saying that is the particles moving in different directions on the grid would have energies that depend on the angle.
Silas believes if we measure cosmic rays zipping through space and find that those traveling at one angle have consistently different energies from those traveling at another angle, then we'll know there's a grid structure to our universe.
It's a glitch in the system, an indication that our universe may be operating in a simulated artificial manner. I think it would cause everyone to think about the universe differently and to really search for an explanation for why there is this grid structure, whether it be a natural one or whether it be due to the fact that we are being simulated.
If we're living in a virtual reality inside a computer, some kind of master code must run all the programs that make up our universe. You would think that code would have to be impossibly complex. But this computer scientist claims he can run the universe from the lines of code on a single note card. Imagine that some entity far more advanced than us could invent computer programs for every aspect of our universe. The behavior of atoms, laws of gravity, the human genome. To manage all of those individual programs, the creator would need some master program, like a cosmic operating system. The software would be impossibly long and complex, right? Maybe not. One German computer scientist claims that these few lines of code are all someone would need to run our universe. Jürgen Schmidhuber is the director of the Swiss Artificial Intelligence Lab in Lugano, Switzerland. He believes our universe could well be computer generated and thinks he knows how to write its code.
I believe it's quite possible that our universe is computable, meaning everything is part of a computer simulation. Now you may say, how could you possibly program the whole universe within fewer than 10 lines of code? Well, there are many things about our world that seem very complex, but really aren't.
Jürgen believes it all boils down to a single core principle: data compression.
For example, this is an incredibly long number, long enough to wrap around the world and come back again, over and over, forever. There's a very simple concept behind it, which is the ratio between the circumference of a circle and its diameter, or pi. There's a very short code, a short program that computes this entire long sequence.
Compressing a giant number like pi into a few characters of code is simple. Similar data compression could be taking place all around us. Clouds in the sky might be rendered by simple equations that generate complex shapes and movements. The same goes for our entire landscape.
Computer-generated fractal landscape programs take small triangles, stack them on top of each other while also rotating and crushing each other on various sides to make very realistic versions of nature. And in a virtual reality, this mountain or similar mountains can be created with just a few lines of code.
A simple repeating program may work fine for building a virtual mountain, but what about living creatures? How about the complexity of human behavior? Can all of our movements and decisions be compressed into simple bits of code? According to Jürgen, what we call learning is really data compression. Anyone who's tried to find a new address in an unfamiliar city knows how complicated that can be. But once the route has been learned, the next trip is easy.
Humans are problem solvers, and any efficient problem solver is going to try to find a solution to the given problem that is both simple and fast.
If Jürgen decides to go to the top of a nearby mountain, he'll use a series of simple programs to get there. Each program that goes into accomplishing the larger task is known as a sub-program.
The first idea that comes to mind is to reuse a subprogram that I learned a long time ago, which involves sending electrical signals to my leg muscles and make them move in a certain way. That's called walking.
The coordinated action of billions of nerve and muscle cells is now a simple sub-program. The same goes for a more complex interaction between man and machine.
It involves a little piece of machinery with two wheels, and again, another subprogram that invokes my leg muscles in a certain way, and that's called biking.
But are there some aspects of our universe that can't be compressed into simple programs? Surely we can't compress everything in our lives. What if he loses his ticket? What if the tram breaks down? Can truly random events be programmed? Jürgen believes that what we see as random or accidental events only have the appearance of randomness. They are what he calls pseudo-random.
So if this universe can be computed by a short program, then by definition it cannot be random. It must be pseudo-random, just like pi, because truly random data is not compressible.
If Jürgen is right, then there is no luck, no chance, no free will. Everything we've ever done and will do has already been programmed. So maybe all aspects of our universe can be broken down into simple sub-programs. But how could a short master program control all of them? Jürgen believes it only takes one final act of data compression.
We just write a very short program which lists all possible programs, starting with the shortest. And the entire list of programs is very easy to generate, and then this master program allocates runtime to each of these, such that all of them get a share of the total runtime.
It's hard not to feel insignificant if we're all just bits of computer code. But Jürgen believes it actually makes each of us more important than ever.
If you change a bit of this program, maybe all of this will completely disappear and the whole universe will be very different. In that sense, you can view yourself as an essential ingredient of the entire universe. It will be very difficult to edit you out of it, because the only way of getting rid of you is to make the whole thing more complex.
If everything in our universe is made from computer code, then the fundamental building blocks of our existence are information instead of matter. If so, can we find those bits and bytes of reality? One physicist claims to have done just that. What forms the foundation of our reality? If you could look deep inside every atom and every ray of sunshine, you'd find fundamental particles, the building blocks of matter and energy. But what are they made of? Could the building blocks of reality be simply bits of information? Theoretical physicist Jim Gates at the University of Maryland investigates the physics and mathematics of the fundamental particles in our universe.
Well, you see, we physicists, you could call us a company called Equations Are Us, because what we really do is write equations that describe nature and then use those to make predictions about things that no one had ever found or seen or even dreamed of before.
Jim investigates how the fundamental particles of the universe interact with each other. Because he's a proponent of the controversial concept called string theory, Jim often finds himself selling his ideas to skeptics. String theory includes at least 10 dimensions of space and many particles that have not yet been discovered. It's all based on some very complicated math.
I found some very puzzling signs that buried in the equations that I was studying, there was another set of equations. We discussed this with some mathematicians, and to our great disappointment, the reaction of the mathematicians were, "What in the world are you talking about?"
To make the equations easier to understand, Jim turned them into geometry. He represented the interactions between subatomic particles as specific three-dimensional shapes. He called the structures adinkras. The name is derived from a West African symbol used to represent abstract concepts.
I could have my equations that I understand the way that I do, then I could put it in front of a mathematician and to ask, what is it that you see here? They will begin to tell me a different story, and that's the power of collaboration, and that's what started happening with us.
Jim collaborated with physicists and mathematicians to examine how the parts of an adinkra structure relate to each other. Buried within the convoluted calculations, Jim found something that looked familiar. It looked like computer code.
It turns out that expressing the relationship between them is easiest if you use ones and zeros. These are called bits in computer science. I know of no other example in the kinds of equations that describe fundamental science where bits have occurred. And even more remarkably, we have found that the bits in our equations arrange themselves into error-correcting codes, something that makes your browser work every day.
When you surf the web or use any form of digital communication, crucial ones or zeros are inevitably lost in the transmission. Error-correcting codes fill in the dropped bits. They protect data from corruption and prevent computer programs from crashing. Jim believes the error-correcting codes he discovered work in the same way to maintain the stability of subatomic interactions. Without this error correction, the way fundamental particles interact could be corrupted, like a computer crash on a universal scale.
Then you can ask, well, gee, does that mean that somehow our universe is like a big computer simulation?
The idea that nature might use error correction codes at first seemed wrong to Jim, but he soon found another example.
It turns out there's one piece of natural science in which this discussion has been going on for decades. It's genetics.
In the human body, error-correcting codes allow us to stay healthy and strong.
The codes act to stabilize the genome.
Genetic error-correcting codes ensure that cells copy themselves accurately throughout an organism's lifetime. Think of the DNA replicating itself while a cell divides as being like a fighter trying to stay strong and stable during a round in the ring.
We can imagine that if our fighter doesn't have error-correcting codes, the first thing that happens is one of his arms stops working. Next, his legs stop working. Then his eyes fail. Without error-correcting codes, he is quickly deteriorating, struggling to survive. There's no stability, and he could collapse at any moment. Now, a fighter equipped with error-correcting codes will eventually also deteriorate. However, the error-correcting codes act to sustain vigor for a much longer time.
When bad copies of genes get made, the results can be cell death or malfunctions like cancer. Genetic error correction reduces the copy failure rate to less than 1 in a billion.
And this is an analogy for the role that error-correcting codes could play in the structure of something like our universe.
Our universe has been running smoothly for almost 14 billion years. Maybe it has lasted that long thanks to error-correcting codes. Codes that make sure the fundamental particles in our cosmos don't go haywire. But nothing lasts forever. The Eventually, our universe will begin to age, errors will creep in, and it will die. Or, what if the codes Jim discovered really are computer-generated? Whoever programmed the cosmos could decide to pull the plug at any moment. Maybe it's time to create our own universe. Is our universe a natural one or artificial? Either way, it can't last forever. So is there anything we can do to save ourselves? Perhaps we need to design our own new universe and move there. Philosopher Clement Vidal of the Free University in Brussels believes we need to take control of our cosmic destiny.
It's almost certain that our universe will end. So should we accept this as a blunt fact? I don't believe so. I think we should do something about it. And if we take inspiration from biology, which is to reproduce, so maybe we should reproduce the universe.
We all want a better life, a better home for our kids. And Clement believes we may one day be able to give our descendants a better universe as well. It's a big project, to say the least. According to Clement, we'll have to practice first by building virtual computer-simulated universes.
In any engineering project, you start by making a simulation of what you want to build. So I imagine that in the far future, an advanced civilization would want to explore the space of possible universes and then select the universe they want to build. One of the most important things we need to learn is how our universe came to be fine-tuned for life, and simulations can help us to learn that.
When the simulations are done and we're ready to build a new home for our descendants, we'll need one more thing: a colossal source of energy.
Indeed, the making of a new universe will most likely resemble another Big Bang. So the energies would be very high, and ultimately this new universe would be disconnected from our own, which means that it would have a new space-time structure.
Making a Big Bang may sound impossible, but Clement believes a special type of binary star system could provide the needed energy. Supermassive stars such as white dwarfs and neutron stars have enormous gravitational pull. If another star is close enough, the more massive star sucks in the energy from the companion star. Clement believes we could harness this enormous concentration of energy. Think of it as an incredibly scaled-up version of a renewable energy plant.
These wood pellets are converted into electricity at this biomass plant. In a similar way, the energy of a companion star is converted into a denser form of energy into white dwarfs, neutron stars.
Imagine this power plant is the size of a neutron star. And these pellets are being harvested from another nearby star. They are so dense that a single pellet would weigh more than Mount Everest. Clement thinks if we can use that enormous concentration of matter and energy, we'll have the power to change the fabric of the universe.
Well, to create a new universe, presumably you would have to manipulate the structure of space-time, and this space-time becomes, in some theories, malleable at very high densities.
Could we someday harness the energy of super-dense stars to manipulate space-time and create our own Big Bang? Clement's theory of universe creation is far from mainstream, but he hopes that someday his concept will be tested.
I'm confident that tests can be devised because we have plenty of data about those interacting binary star systems. So we just need to think creatively and scientifically about how to test the hypothesis.
The first tests will no doubt be done through computer simulations. Perhaps some other civilization more advanced than ours is already conducting these tests with us. Are we living in a universe created by someone or something else? If so, is it a beta version that an advanced entity is still tinkering with? Or is it a version they've programmed to last? Maybe someday, we'll find proof that we're all players in the greatest video game ever made. Would that knowledge make us feel manipulated like pawns? Or would it free us, take risks, and live life to the fullest? Because none of this is real. Either way, whether it's natural or artificial, life is a glorious game, and we should play to win.